Hello again, folks, in 114. Today I'm going to be covering section 7.3. The calendar for today. Let's see, today is Wednesday, June 9th. So we are covering section 7.3. Very good. The packet of material consists of this overview page. I left these spaces blank just because I figured I would give you a little information. And we'll discuss this. This is, we're going to be covering mass and weight to distinguish those. And this is an older diagram I had made from ages ago, just to explain what a ratio is. That'll be available. And this is more pertaining to the actual section 7.3. The differences between Fahrenheit and the Celsius scale for temperature. An overview. Then there are the things I swiped, some tables and diagrams from the textbook in case you prefer this. And some examples, which I will paraphrase. All right, we'll go through this. Alright, so if you're following along, do print that out. We'll get rolling. It's a bit of a late start today, admittedly. It's like 12:30, something like that. No, it's afterwards. I'm sorry. The weather is kind of inhibiting me a bit because it's hot here. Forgive me. Anyhow, let's get rolling. Turn this on and make the necessary adjustments. In the right place. That's a little too much. That's fine, leave it like that. Okay. Here again is the overview from the beginning of chapter 7. Not to be redundant, but just to keep things in order here. We are discussing metric units that are for different physical measurements. And we have to this point covered one-dimensional measurements, which are distances, basically. Remember, distances can be called, depending upon the circumstances, a side, a length, a width, a height, a depth. There's different words for them in English. This is step 1. Material. And then yesterday we had covered this, section 7.2, which is a difference between things that are one-dimensional and basically things that are three-dimensional. Capacities are volumes. Right. The primary unit for capacity would be the liter. It's the natural base unit. Alright, you could, if you wanted to, because of the relationship between lengths, widths, and heights, being that they can form a volume as well, you could express a volume also in cubic meters as opposed to meters to the first degree. It's an alternative, and if you're talking about a solid or a gas, that might be appropriate. But this is the base unit. Now what we're going to do today, I'm not sure why this is highlighted. These two topics, mass and temperature, are the subject of 7.3, which is where we are, of course. Right? The unit, the base unit for mass is the gram, and the base unit for degree is the degree Celsius. Right? Come to think of it, I've never seen millicelsius. All right, they really don't. When it comes to temperature, we don't do that, right? We don't have a millidegree or a nanodegree or anything like that. We just use the temperature scale, or we opt for a different temperature, which would be Kelvin. All right. Okay. Now, although I did leave space here, and if you'd like to, you could fill in some interesting information here and here for those subjects. If you want to keep everything all on the same paper, I actually made a new diagram that is specifically for these things. So let me show you that. Okay. I should put my glasses on. There you go. Okay. Okay. Now, these are often confused or conflated. The subject of weight and mass, right? But here's the distinction and how you would help identify these. Weight is proportional to mass, right? They are related. Weight is proportional to mass, which means what? It means that weight is dependent upon mass, right? Remember back from MAT-113, right? If you had me for MAT-113, then you very likely had seen this model. That's a terrible green. Y equals K times X. And I purposely put these in different colors to show you that, remember, they sit in different places and they have essentially different labels. All right. In MAT-113, let's see if this actually writes. That's not so bad. In MAT-113, section 6.4, that looks like it's fairly visible. This subject was introduced, all right? A model that you could adapt, all right, for when the relationship between two variables, x and y, is directly proportional, which basically just means that you're at worst multiplying, right? K is known as a proportionality constant, right? The other forms that we had were inversely proportional, or I'm struggling to remember right now, but in which case you have the variable x would be a denominator as a fraction. There are two other examples. One is a composite of those two, inversely and directly proportional, or if you had a third term in theory, a third factor. Anyhow, weight is essentially directly proportional to mass, right? So they're not the same thing, they're just very strongly related. Another way of saying that is that weight is dependent upon mass, right? Because of this arrangement, right? But they are not the same thing. Now, to give you a little bit of space, all right, let me move this up. And I'll just remind you, all right, in MAT-113, section 6.4, this would have come up, this idea of proportionality. This phrase, dependent upon, as in dependent and independent variables, would be from our semester, MAT-114, right? Section 610, I want to say. So there are different ways, right, to think about this relationship, okay? This is more verbal, this is more algebraic, the way it's written here. Okay, now, to further elucidate, there's some space here on purpose. All right, what is true physically about these two things that makes them distinct? Mass does not, emphasis on not, vary with location. Right? Your mass on Earth is the same on the moon, say, for example. Right? It might, in theory, change. No, it will never change. Your weight might change, all right? But your mass will be consistently the same no matter where you are, all right? Officially, the definition of mass is, if you've never taken a science class, the amount of matter an object is comprised. Comprised or made. That's mass. The amount of matter of which an object is made, right? And it will consistently be the same, right? No matter where you're standing, okay? It does not vary with location. Your mass on the Earth, for example, is the same as it is on the Moon. Now, as far as weight is concerned, right? This does vary with location. It is actually dependent upon gravity. To use the more plainer phrase. And gravity really depends on proximity. To the center of a, say for example, a planet. In theory, right, the further away you are from the center of the Earth, right, the less you will weigh. So if you were to somehow be able to weigh yourself at sea level, right, and then teleport, that is, don't really do any exercise, but weigh yourself on the tallest mountain, you know, at the very top, right? You should, in theory, weigh a little bit less, right, on the top of Mount Everest, right? Only for the fact that you are further from the center of the Earth, right? Because gravity, which decides weight, all right, in tandem with mass, depends on proximity to the center of a planet. I hope that's not too faint, because my blue is dying here. The definition of weight, if you've never taken a physics class, I'll try to make this talk. Pardon me, weight is the force, and may it be with you, and also with you, right, due to gravity exerted upon a mass. This will make more sense in a moment. All right, but let me just, that is really faint. Oh, brother. It's barely visible. I don't think I'm going to be using blue today. All right. I'll just darken this a bit. All right. Weight is the force due to gravity. Exerted upon a mass. These are two different concepts, gravity. They're two different factors, as a gravitational acceleration, right? And a mass, which is measured in kilograms, usually in physics class. Anyhow, let me show you some conversion factors in a moment. I didn't unfortunately give myself a lot of space here. Let me see if this makes it a little bit easier to read. I'm not sure that it is helping. If you want a freeze frame, if you're inclined to record what I've written at the top there, now might be a good time. Let me, before I move this down, just show you one other thing. I'm very short on real estate here, so what I'm going to do is I'm going to erase this just to show you how we would adapt the directly proportional model, right, as discussed in section 6.4. Right? If this is the model really trying to just squeeze in some information here. If the model that we have is y equals k times x, right? To adapt it to the concept of weight, what physicists have done is basically put the actual independent variable up in the front, right? And moved the constant, the proportionality constant, to the back, right? It's commutative, it just involves multiplication, so just swapping the position here and here doesn't matter. All right, this is still y. And then change the labels. So if weight is a force, then a logical letter to represent, to stand in place of the dependent variable y would be f. All right? If you want to identify it specifically as the force of weight, you might use a little subscript, so a w here. And instead of the independent variable being labeled x as a generalization, let's use m for mass. So maybe I'll just make that red, that would be intuitive, right? And the proportionality constant is known as lowercase g, right? Which is acceleration due to gravity. Now that depends on what planet you are standing on or what body. On the Earth, it is famously negative 9.8 meters per second squared. So if you wanted to, although your mass would be in kilograms, right? You could calculate what your weight should be in newtons, right? Because in a physics class they don't use pounds, they use newtons, all right, of force. All right. Anyhow, as you can see, it is essentially two factors that are multiplied. We've just switched the positions and we've changed the labels from the model, all right? These are directly proportional because all it involves is multiplying, all right, two factors, and one of them is a constant. 9.8 is considered a constant, the acceleration due to gravity, in this particular scenario. All right. Anyhow, you are not really responsible for this, but you're certainly capable of grasping it. And I think it would give it a little bit more meaning if you relate it back to something that we've already discussed. Some things that are directly proportional, right? Right. The model could be adapted to explain the concept, right? And it illustrates that weight is dependent upon force. Weight is dependent upon mass, right? Weight is the force. If you don't like F as a generalization, you could put, as a label, you could put W for weight. This might be more intuitive. Weight is dependent upon mass, all right? Okay. Now, as for the conversion factors, what would be good to know are these. When you're converting between the metric system and the imperial system, notice that there's a squiggle here. Because this is, the relationship is rounded. All right. 1 kilogram is approximately 2.2 pounds. Right? If you were to rearrange this relationship, right, it would be something like a half a pound is, or 1 pound is about 0.45 kilograms. Let's see if I can get here really quickly. Yes, there you go. If you were to approach this from the perspective of pounds instead, you would divide 1 by 2.2. And you see that it's this repeating decimal, so it's not quite right. It's something you would have to round. Approximately 1 pound is a little less than a half a kilogram, so 0.45. I think your book probably favors writing it that way. Sometimes when you're converting, it's more appropriate to write things in this orientation, and sometimes it's more appropriate to write it this way. Even if you just had one or the other, you could make it work. Right? Slightly less familiar to an American, perhaps, would be this unit. The metric ton, which is spelled this way, Americans, T-O-N-N-E. All right, we have the ton, but the spelling should help us differentiate. Right, distinguish one from the other. A little bit more subtle is that the metric ton is abbreviated as a lowercase t. Sometimes it's italicized. The American or imperial ton, T-O-N, is a capital T. All right, they're not the same thing in spite of their similarity. All right, 1,000 kilograms is the equivalent of 1 metric ton. Right, 2,000 pounds, coincidentally, is equal to 1 ton. Okay, so you could, in theory, convert tons to metric tons if you tinker with it. All right. You can always tinker with it to figure it out, but I'm not going to do that right now. There's something that I keep thinking of that's slipping away from me. If you're curious why this, obviously kg is for kilograms. If you're curious about lb, why is pounds, which we spell with a p here, why lb? It's from Latin. Remember, this is ancient, a lot of it. The concept, even if we have refined the definition over time, still is derived from Latin, and this is libra pondo. I believe is the spelling, lb. It means literally 1 pound weight. If you're familiar with astrology, perhaps a person who's a Libra is famous for. Libra is symbolized as a constellation holding the scales. Right, that's measuring things. Right. Anyhow, what you see here in this first sort of blurb bubble here is generally true. Right. So I put purposely, I wrote in general with a little callipy here to squeeze this. You will use these, right? And you don't really have to worry about any other definition or specification, all right? Down here is another story, all right? The scientific definition of a liter is that a liter and again, I'm spelling it the American way, is 1 kilogram of water at standard temperature and pressure. Now, I believe, don't quote me on this, but I want to say standard temperature is 0 degrees Celsius. You really don't have to worry about it. Standard pressure is 1 atmosphere, which is the pressure outside at sea level. If you go up in the mountains, pressure changes. Anyhow, that's the definition. A liter, 1 liter, is historically, is 1 kilogram of water specifically. All right. The volume of 1 kilogram of water 1 liter is the volume of 1 kilogram of water at standard temperature and pressure. You don't really need to dwell upon it, but it is derived from that, at least historically. So these relationships are true for water under those specific conditions. All right. Again, you probably in our class not going to have to worry about, you know, atmospheres, all right, or whatever alternative unit bars, you know, millimeters of mercury or so forth, all right, or that you're using the Celsius, all right. But, all right, just realize that this is derived from a volume, a cube, if you will, of water, all right. All right. So this is specifically 1 cubic centimeter. How much would it weigh? I shouldn't say weigh, but how much mass would it be? This is a relationship between a volume and a mass, right? We wouldn't normally blend those two concepts together, right? But it just so happens, because of the definition of water, volume of a liter, you can calculate, right, the mass of something knowing its volume, at least again under those specified conditions. Okay, so if we're talking about water, all right, you have 1 cubic centimeter of water, should weigh 1 kilogram, all right, or thereabouts. If you had 1 cubic decimeter, all right, it would be equal to 1 kilogram. If you had 1 cubic meter of water, all right, which would be like, you know, a very squarish, a fish tank or something like that, that'd be equal to 1,000 kilograms, right? Which we have established is 1 metric ton. Right? Water is quite massive. Right. All right. So definitely keep these tables on hand. They're printed elsewhere in the packet, but it occurred to me to group these in proximity. Okay. All right. Now let's do some examples. All right. And I'll turn this off. I feel like that's fading a bit. I hope it isn't. My bulb's getting weak. If you look in the packet, maybe I should spare myself the trouble and actually project this. Let's look at the example that would be example 2 from the packet. Right, this fish tank. Yeah, I think what I might do is I might actually turn that back on. I think the lack of oxygen and the heat all conspiring to make me less and less decisive. Anyhow, let me pull this up and I'll try to stretch this a wee bit. Okay, that's a little bit better. Just zero in on the fish tank that you see here, and we'll discuss this. All right, everything that is pertinent is visible. Maybe I'll just lower the not noticeably. We're going to calculate the volume of the fish tank is the drawing. It's a very lovely looking goldfish. All right. Given the conditions that the fish tank is 1 meter long this way, 50 centimeters tall or height, and 250 millimeters wide. All right. So it is essentially, even without the picture, long, high, and wide, implies that this is a volume of a rectangular solid. Right, now do notice something. The author of the problem has intentionally given you these units inconsistently. They're all legitimate one-dimensional measurement units, so centimeters, meters, and millimeters, but they're not all the same. So even though we have established the formula, of course, that volume of a rectangular solid is the length times the width times the height, we can't actually multiply them yet. We would have to convert them. All right, which is not too difficult. All right, remember, when you're converting between things of the same dimension of the same system, all right, you really could just use the scale if you'd like to immediately. Since we're talking about meters, right, we can convert meters to millimeters and so forth. As long as you remember them in the appropriate order, you're okay. And eventually you won't need the scale anymore. All right. Now, my instinct is make everything meters. All right. That means that you would just need to worry about converting this unit here, centimeters, and millimeters here into their equivalents. All right. Now, if you're a little rusty, all right, if you start at centimeters here and you convert to meters for the sake of consistency, you're going to move your decimal point 2 times to the left, which means that if this is 50 point, right, you would scoot your decimal point over twice and you'd have a half a meter. So 0.5 meters is what you have instead. Right. If you're going a little bit further along, millimeters, and you're starting here, then to convert it to meters for the sake of consistency, you're going 1 extra step. This is going to be 3 jumps. So if you have 250, the decimal point would be here. Going towards the left, you would go 1, 2, 3, and you have a quarter, basically, of a meter. Right. Now, if you wanted to, you could calculate the volume right off the bat. Right. So let's do that. All right. If you have a length of 1 meter, and you have a width apparently of a quarter of a meter, 0.25 meters, and you have a height of 0.5 meters, all right, then you know, according to the volume formula, that even though it would be expressed in so many meters cubed, we will definitely have a volume, and then we could make the adjustment to liters as an afterthought. All right. So 1 times these things is not going to change anything, right? Right. So it's really a matter of doing 0.25 times 0.5. All right. If it was just 25 times 5, you would have 125, right? As far as the digits are concerned. Since there are basically 3 decimal places to consider, from here to here you would have 0.125 meters cubed, right? At least to begin with. Okay. Now, since the first question here says determine the number of liters of water, we would have to adapt cubic meters into so many liters, right? Now, right? And in that event, let's borrow the information that we have established. All right, from here. All right, we have a relationship between cubic meters and kilograms. And kiloliters here. So let's see what we have. We're going to have to sort of go forward and then backward. Since we're starting with cubic meters, we can convert cubic meters directly to kiloliters. That's still not quite what they're asking. They want liters, the base unit, not the kilo unit. But we'll get 1 step further, right? And in that regard, right, let me just minimize this for a moment and remind you of that conversion model that we have. Right? I'm going to maybe borrow the bottom longer version of it. I'm not going to use this many conversion factors, but I'll use what is necessary. All right. Now, what is given in this case is this figure here. So appropriately all the way on the very far left. All right. And what I can convert to is I can convert cubic meters into kiloliters, right? According to, again, that conversion factor, right? Remember, you always consider 2 at a time in the style of a fraction, whatever is convenient for you. Right? So if I want to cross cancel cubic meters, I'm going to put cubic meters down here, right? And if I have a direct relationship to kiloliters, that's just the way it is, all right, then I will put that above the line here, all right? That, once you decide where the units go, will direct you to put the actual figures involved, the 1 and 1,000, in the appropriate places. So if you have 1 cubic meter, that would go down here, and the relationship to that is 1,000 kiloliters, all right? Well, already what you can do, although I'm probably jumping the gun a little bit, is I can illustrate that this cross cancels the unit that you have to work with, right? And since this is 0.2125, if I were to make it look in the style of a ratio, I could just stick a 1 under it, right? And the effect would be that I would just multiply 1,000 times 0.125, which really spitefully throws the decimal point right back to where it was, right? That will just give you kiloliters, though. If we're going to go the whole 9 yards, which is to convert it to what they've asked, we would have to eliminate kiloliters. So I'll put kiloliters down here for the sake of cross cancellation. And then what I want, I could definitely relate kiloliters to standard liters. I'll put liters up here. Okay, now what is their relationship? 1 kiloliter is 1,000 liters by definition, right? So if I rig the machine this way, I'll just try to make this a little less distracting by erasing this. I get the satisfaction once again of canceling out kiloliters, this unit and this unit. Always one above the line, one below the line, not next to each other. All right, that means that I'm going to multiply by 1,000, and then I'm going to essentially multiply by 1,000 again. Why so? Because if the denominators are all 1 times 1 times 1, that's just going to be 1 here at the end, and that's superfluous. It's not really necessary. And then it's just the top times the top times the top. The effect of the first 1,000 is to scoop the decimal that far. The effect of multiplying by yet another 1,000, just because we have to, would be to add another 3 waves. So what you should end up with is something quite large here. That doesn't make sense though. All right. There's a boo-boo somewhere. I'm off by a decimal place somewhere. You can't have 125,000 liters into a fish tank. I'm sorry, that's just not going to happen. For shame, Ziegler. I'm sorry. I see what I did. Let me, see, scribble doesn't really help the situation, so I'm going to do this a little bit further up, a little bit neater. All right, forgive me. This is what we have to start with, 125 meters cubed, all right? And we have a relationship, all right, which I keep pointing to and I'm ignoring it when I shouldn't, of this being 1 to 1, right? Not 1 to 1,000. All right. I didn't even take my own advice. It's shameful. So yeah, right. The unit of meters cubed would go down here, and kiloliters would be here. But I chose the wrong numbers. 1 cubic meter is 1 kiloliter. Right. This much volume for the amount of water at standard temperature and pressure is this much mass, coincidentally, at standard temperature and pressure, all right? So when I added the extra conversion factor here, I included too many thousands is the bottom line. So I'm gonna cancel kiloliters here and end liters there. The relationship I mentioned at this point is correct, right? In 1 kiloliter, there are 1,000 liters, right? But the bottom line is this: there was not needing to be an extra 1,000 here. I jumped the gun a little bit, and I incorporated this in 2 places. So I'm sorry for that. Anyhow, here we have the machine good to go. Again, the bottom is 1 times 1 times 1, which is unnecessary really to have as a 1, but if you're treating it like ratios, then that would be appropriate. All right. The units, meters cubed, are rigged to cancel here and here. And the units kiloliter and kiloliter are rigged here and here. All right. Then if you deal with the top, it's 0.125 times 1, which doesn't change anything, right? Then times 1,000 just at one time. And again, the effect is that it just throws the decimal point back that way. Right? So you end up with equals 125 liters. Right? And that's it. Okay? Sorry for that. All right. If I can't set a good example one way, I try to do it another way. Neatness helps. All right? One thing you'll notice as a teacher too, it's unfortunate when you're trying to explain something that you're this close to the thing that you're writing on. It's kind of the equivalent of if you had your head on a desk and you're writing like this, because if you could just stand back a little bit further and look at the entire forest rather than the individual tree, all right, you'd be less likely to make a mistake. All right, so don't get mad at yourself and don't get mad at your students. All right, all right. Proximity to where you're writing helps. You know, distance is important. Okay. So, that was the first part of this. 125 liters. And now what they'll be asking us is, well, what would the mass be? You would again consider your conversion factors, just choose to read them correctly. 1 cubic meter is equal to 1,000 kilograms. See, that's what I did. I jumped from here to there, right, rather than looked here and here the way I'm supposed to have. Okay, so what we can do is we can rig up another little machine here. I'll see if this writes visibly. What is given, you're going to multiply by a conversion factor, and if necessary, a second conversion factor, I don't know yet. And that will spit out what you want as a system. Okay, that is very faint. Well, what do we have to work with? We do, in theory, have still that original figure, 125 cubic meters, right? And we know that we can convert, according to our list of conversion factors, cubic meters into kilograms. Right. And since that's what they want anyway, that would be totally appropriate. So we won't need another conversion factor. Let's just make sure that we put the numbers in the correct places. Right. 1 cubic meter is equal to 1,000 kilograms. 1 cubic meter of water at standard temperature and pressure should basically have the mass of 1,000 kilograms. So again, if you're treating this like ratios, that is a glorified fraction. It's 1 times 1, which doesn't change anything. Right. And then 0.125 times 1,000, again, just has the added effect of moving this decimal the other way. So what you would end up with is the same figure, 125 kilograms. Right? Isn't that interesting? The volume in liters is 125 liters. The volume in, the mass of that volume in kilograms is 125 kilograms. That's probably not coincidental. That's because of the definition of a volume of water. Right. Okay, it's essentially 1 to 1. In this case. Okay. I'll leave it, well, as you can see here from this, I'm sorry because I know it's 3 things at once, but if you look at this slew of conversion factors, yes, this is 1 cubic decimeter. But what you're supposed to do is you read these as 2 at a time. Right? So if you read these just 2 at a time, notice that the relationship is indeed 1 to 1. 1 liter would be equivalent to 1 kilogram, which is why 125 liters should be 125 kilograms. Okay. All right. And there you have it. Very good. Okay. Notice that your book is using a lowercase script L rather than a capital L. If you take a chemistry class, you're more likely to see a capital L. Okay. All right. While I have the opportunity, let me show you this other slide, which has to do with ratios. Because I keep saying, when I tell you about this unit conversion model here, I've said this, and I mean it. A conversion factor, which is those equations, 2 at a time, oriented in the style of a ratio, right? Or a rate in this case, is a glorified fraction. And by that I mean it has an obvious top and it has an obvious bottom. But it's strategically rigged for the sake of a cancellation effect. Right? When you get comfortable with it, you're enthralled with it because it helps you like a little machine that you're setting the dials on. You know? And then you let it run. Right? You have to check your work, as you can see. What stopped me myself just a few moments ago was that I reasoned to myself, no, it's not possible to have 125,000 liters into a fish tank. It's a highly suspicious figure. Anyhow, a ratio is the more correct word for a conversion factor oriented that way. All right? When you have an obvious top number over an obvious bottom number, this would be most generally referred to as a ratio, right? We think of that really as a fraction, right? But the truth, that's just an ordinary way of speaking. A fraction is a little bit more strict technically, right? A true to form fraction has a top and a bottom, right? But you never see a decimal anywhere in the top or in the bottom independently. You know, it's always, even though the whole thing represents a decimal, the individual parts are not decimals, right? So it's always unitless if it's a genuine fraction. And there is a non-decimal figure on the top and also a non-decimal figure on the bottom. All together, they represent a decimal. All right, now, a lot of times when you have something slightly less strict, right, you might have it oriented using this symbol, right? What would normally be the top, we're going to call A, and what would be the bottom will be maybe intuitively B, all right? In other countries, when they teach, I mean, outside of the United States, when they teach the subject of division for the first time, this is the symbol that they would use, right? In the United States, we're inclined to use that, a colon with a line through it to imply division, right? But elsewhere, they might just use the ratio, what we refer to as the ratio symbol, right? The colon, right? So if you see it written, you know, and more verbally than sort of mathematically, right? You might see a word and then a colon and then another word. Or if there are English words thrown in place of that, there's two options that you have. You could say a and then the English word to, or a little bit more verbose, you might say out of, right? So for example, 1/3 be 1:3, or you would say 1 to 3, or 1 out of 3. And you could, again, in this instance, use any type of numbers. It could be a decimal figure here and a decimal figure here, all right? Because it's a ratio, not a fraction, which is stricter, all right? Okay? Then there are these phrases you get heard, you get mentioned. There are rates, and there are unit rates, and then there are things called unit prices, all right? A ratio is a rate is a ratio, all right? But the difference is, again, ratio is the ultimate in generalized terms. A rate is something that has different units. There are two different units measuring different concepts, all right? So, and by different concepts, I mean they measure different physical concepts. So when you see a street sign like miles per hour in the United States, a lot of times it's abbreviated MPH, right? If you saw it instead in the style of a ratio rate, it would be mile on top, a line, and then hours underneath it. Now this is getting at the heart of what I'm saying here. They measure different physical concepts. This unit above the line measures a distance, which is a one-dimensional concept, right? This unit down here measures time, which is not a physical distance, right? It's the fourth dimension time, really, right? But it's a different physical concept, right? As long as they're different physical concepts, you have a genuine rate, right? If you have something that maybe has different units, like for example, even if it was, 2 inches sitting on top of 3 centimeters, right? Those are different units, but they still measure the same thing. They measure a length, they're not different physical concepts. And one could convert from one unit to the other. That is really the subject of section 7.4, all right? But then you could cancel out the units eventually. That's what happens very often, the units cancel. Right? If you have a rate, you can't cancel these units because they measure different things. Right? A unit rate is the same situation, but the numbers are actually divided for the sake of simplifying. So what you end up with is you write their quotient. The quotient becomes the top, and then the number 1 becomes the bottom. So whatever decimal or whole number in theory that you get as an answer from actually dividing, you write that above the line, and then again, for the sake of simplicity, for a unit rate, you would put a 1 as the denominator, and then include whatever unit and unit here and here, right? Now, if you're talking about money, there's this concept called a unit price or a unit cost, whatever. All right, that is the same idea as a unit rate. It's for the sake of simplicity. But it's regarding money, right? So it's a little bit more strict. You have to have the top number representing an amount of money. So if you had, $3, you know, per, I'm trying to think of a banana, no, that's silly. $3 per dozen or something like that, per 12, you know, eggs. That's kind of expensive, but whatever. You could write this in the style of a glorified fraction known as a ratio. And because you're dealing with money, money has to be on top. Usually that would be the intuitive way. This is, you know, comes up first in a sentence or a fragment, all right, and the 12 follows it. So you would do that intuitively anyway. But if you're talking about a unit price, you would have no choice. You would have to defy anything that is counterintuitive and purposely put the money value on top. All right, so then if you want to, you would, to make it a true unit, right, you would divide these. All right, you would have to divide 3 by 12, all right, which you would end up with, think of it in the style of a fraction, simplifying it, this becomes 3 divided by 3 is 1, and this is, it's the same as $1 for 4 eggs, all right, but even that is not finished, all right, that is 1 divided by 4, which is 0.25, right, over 1, right. So what we would regard in the United States as 25 cents, $0.25, the quotient becomes the top, and 1 is the bottom for the sake of the unit, right? So a quarter per egg, you know? Anyhow, this is not really the kind of thing that you have to worry about now, but as a teacher who is teaching kids who are, you know, in elementary school, all right, try to make, you know, extra, you know, try to make the point of clarity, you know. I'm dying of heat here. Take the time to be extra clear, you know, the students will appreciate it, all right. This may be the way that we speak of things that look this way, as a top over a bottom, a number sitting on top of another number. And when you speak in ordinary conversation, that's fine. But in math world, you should try, you know, endeavor to be extra precise, right? So when the word you should really be using is a ratio, right? If you're just generalizing any number sitting on top of any other number. And the conversion factors that we have are technically ratios. Let me go back to this page here. What you see here, although they're not written in the style of a fraction yet, you can write them that way. All right? And you would want to write them that way. So for example, when you have something a little bit more interesting, this one here, 1 kilogram, if you were converting it to so many pounds, right? Even though, yes, this is a mass, and yes, this is a weight, and these are not the same thing, weight, because of its relationship, it's proportional to mass. That is, the more massive something is, the more it weighs. We can get away with writing a conversion factor, all right? In the style of a ratio, I should say, would be, you could either write it like this, 1 kilogram is 2.2 pounds. Or, if it is more practical, switch the position of these around, right? So you would have 2.2 pounds is 1 kilogram, right? Always do these in sets of 2. So like earlier when I made my mistake, right, and I borrowed this number when I should have borrowed this number, right? If you're going, I wrote this as 4 things in sequence here because it is true. This is equal to that, it's equal to this. If you're going to write a conversion factor, right, you do 2 at a time, right? So in this instance of relating cubic meters to so many kilograms, all right, you would write it like this. Either 1 cubic meter over 1,000 kilograms, or, again, you could switch these around, all right? 1,000 kilograms on top of 1 cubic meter. The beauty of this is that you could switch these things around at will, all right? And you would want to because it makes your life easier when you get acclimated. Okay? Enough belaboring the point. All right, now let's get into temperature. Slowly losing consciousness. Okay. The temperature scales that we are inclined to see here in the United States are these two. The official scale that we use here is still the Fahrenheit scale. All right. The Celsius scale is virtually anywhere else on Earth, and we really should get on board. There is, in theory, this is why I put this thought balloon here, there's another temperature scale which you don't see outside of physics, maybe chemistry, which is the Kelvin scale. It's very interesting, actually. It's based upon the concept of absolute zero, which is the temperature at which matter does not move in any way, shape, or form. It's truly cold. Right? Anything to a scientist, there's no such thing as coldness, really, unless it's absolute zero. Anything above absolute zero would be considered warm, you know. Because at the molecular level, or the atomic level, things are moving, right, whether we see them or not. Anyhow, the unit of Fahrenheit is the degree Fahrenheit. The unit of Celsius is logically the degree Celsius, or degree C, right? They're contemporaries, all right? Interestingly, it's the same digits, just an anagram of each, all right? This is named for Daniel Fahrenheit, Daniel Gabriel Fahrenheit. He was a German dude who was living in Poland, or what is today is Poland. Judging by the date, there was this country, believe it or not, at one point, the Holy Roman Empire, which, as someone else has said accurately, was neither holy nor Roman nor an empire. Just poorly named. Anyhow, that used to encompass Central Europe, which today would be technically Poland, I believe. At least part of Poland. Anyhow, this was a German dude. Anders Celsius was a Swede. All right. I always like that name, Anders Celsius. If I had a kid, I think I might name him that. That's just an interesting name, Anders. Anyhow, it's very difficult, unfortunately, as an American, to convince your fellow Americans that, hey, you know, we should try this other scale because it's scientifically based. And the reason for that, I surmise, is that we have a relationship to numbers whether we realize it or not. We do things rather intuitively here. Here's what I mean. If you said to an American, your standard ordinary ran into an American, oh, it's 20 degrees outside, and they weren't living with you, they would have a visceral reaction to that. They'd go, ooh, brr. You know, why? Because we associate this number with a feeling, right? That's the hard part of our job as a teacher, trying to get people to not associate the number with a feeling that is already deeply ingrained. It's a conditioned feeling. You tell an American it's 20 degrees, they get, oh God, it's cold. You know? So that's what you're up against as a teacher. You're trying to uncondition people. All right? If they grew up with this idea of 20 degrees being on a Celsius scale, then they would go, oh, what a nice day it is, you know? Why? Because 20 degrees is really 68 degrees, right? These are the same. These are the same feeling, all right? All right. So make that be aware of that. All right, 68 degrees Fahrenheit is approximately 20 degrees Celsius, all right? So hopefully in a generation or two, we will, if not sooner, we will realize that we're, the reason why people are resistant adamantly to changing from one system to another is because you're fighting their feelings, all right? So it's hard, all right? Now, what are these things based upon? Essentially, the Fahrenheit scale is based upon the boiling point and freezing point of water. I think originally
Daniel Fahrenheit might have used like a pickle brine or something like that, all right, which is water with salt in it, but you know, if not other things. But essentially, this is the idea. We're going to consider the freezing point and the boiling point of water, and similarly, Anders's Celsius scale considers the boiling point and the freezing points of water. All right. It's just that they have them calibrated differently. All right. If you were to consider the scale, that is the thermometer, which is why I put the scale vertically. On the Fahrenheit scale, the freezing point of water is 32 degrees. Well, at least 32 and under. And 212 is boiling. All right, point of water. Why those two numbers? All right, because it turns out they're 180 degrees apart. All right, which don't quote me on this. Why that number? Because it's a familiar number. All right, I know that we think of degrees as a geometric, you know, in geometry is a topic of math that is ancient. All right, 180 degrees is, you know, probably a figure that is derived from Babylonian math. You know, remember their number system was based upon 60. All right. Because of their hands. They didn't count their hands as 10 digits. They counted the increments in between, the segments of the fingers. Right? So there's 12 on one hand, and then you use the other hand to count 12s. There's 12 segments on this finger, on these fingers, and then you use the other 5 as 60, right? 180 is a number that is basically a multiple of 60, right? Anyhow, this is a familiar number to the author of the scale. So, and interestingly, geometry uses degrees, right? We're using a degree in a different context. We're talking about temperature here, but this is the way it is. The difference between 212 and 32 is 180 degrees, all right? This is more decimal based, as you can see, all right? This is the freezing point of water, 0 on the Celsius scale, and this is the boiling point of water on the Celsius scale. All right, and the way that it is calibrated is so that the distance between these is exactly 180 degrees apart. All right, this is the reason why, in theory, it would be a better scale. Why? Because it's easier to count in a system that is based upon 10. Right. It makes the math easier, right, in the long run, even if not immediately. Right. Anyhow, there's a formula. If you needed to convert, given the Celsius temperature, right, to Fahrenheit, this is set equal to Fahrenheit. So you would use this formula to do that. Right. If, on the other hand, you were given the Fahrenheit temperature, you would use this formula to calculate the Celsius equivalent. Notice that there is a parentheses here, which means that you would have to do the subtraction first, right? In the case of this formula, there is no parentheses. It's not a typo, right? Which means you really would have to do this multiplication before you add, okay? All right, let me show you something. We'll do some examples and then I'll stop. In the stuff that I borrowed here from the book, there are these nice tables. The same information essentially, but this is useful, I felt. Right? It's sideways, I'm sorry. I can rotate this. Often when you buy a thermometer in the United States, they have both scales written on the same stick. Right? So you could read them. Right? But this will give you an idea of how these are calibrated. Right? Right. Notice that this is the Celsius scale. So although it has gone a little bit lower, because we live in a place that occasionally is lower than 0, lower than 32 essentially. Right? Here's 0 and 32. Right? approximately, on the same tier, all right? But because of the way that they're incremented, all right, this goes up to 100 as the maximum here. Boiling water, it has thankfully never been boiling on the surface of the earth in my lifetime. I hope not anytime soon, though with the rate we're going, maybe that will happen. I hope not. And up here you see 212 is the maximum. Okay. All right. Now the table that is immediately underneath it is to get you as an American more comfortable with what correlates here. Again, 20 degrees is a nice day. You know, it's a nice temperature, 68 degrees, room temperature we would call it. 0 on the Celsius is what we regard as, oh, it might snow, you know, even if it doesn't stick. And a very cold day, all right, we would call 0 degrees Fahrenheit. Remember a couple of winters ago, we had, you know, like a month of January that was like consistently 0 or lower on Fahrenheit, all right, a scale, which would be like negative in the Celsius range, okay? And again, here are those formulas, if they're maybe a little bit more clear here and here. All right, just remember, all right, you have to follow the order of operations when you're working exclusively on one side of an equation. Why? Because this is an expression. And expressions follow the order of operations. It's only when you start moving stuff over and equals that you employ algebra, right? Opposite operations. All right, let's do some examples. I think I might be able to turn off my projector. Let me see. Yeah, you know what I'm going to do? I'm going to paraphrase question 4 and question 5. So let me please spare my bulb. Here. And I'll finally turn the light here and let's in the area so I can breathe. Okay. From the packet, let's take a look at what would be example 4 and 5. Wish I had a third one. All right, we'll do these because these are the conversion questions. Are we on time? Okay. So for what would essentially be example 4, right, let us convert 55 degrees Fahrenheit to so many degrees Celsius. Right. If this is what we are given, 55 Fahrenheit, that's funny how that's very blurry. It's because of the light source side. So odd. I never noticed the shadow as I'm getting right now. Looks like everything is embossed, doesn't it? Maybe I'm losing my mind. Anyhow, the formula for Fahrenheit, since that is what we are given, is this. Right? Fahrenheit is equal to 9/5. Oh, well, converting this, I'm sorry. 5/9 times the given Fahrenheit minus 32 degrees. Okay. So if we plant basically 55 in here, right, and we will subtract first according to these order of operation parentheses here. The difference would be what? 323. Which means down here you'll have the fraction of 5/9 times 23/1. If you could simplify, whether directly above and below or more likely diagonally, I would. It's not going to happen in this case because the common factor of 9 and 23 is just 1, so it's not going to change anything. And similarly this way and this way. So you're kind of stuck with what you have. All right, you could do some brute force multiplying, or you could use a calculator, but just realize that if you're going to do it the old-fashioned way, it's top times top and bottom times bottom, which means that you would end up with a 9 down here and then whatever 5 times 23 is, 15, so 115. Right, now, that's not very satisfying because it's an improper fraction rather than a decimal, which most people like, especially on a a temperature scale. So, again, if you're doing it by hand, 9 stays here, 115 goes here, put in a decimal point, throw in some zeros to get rolling, and be consistent. All right. 9 goes into 11 roughly one time with 2 left over. 9 goes into 25 roughly twice, which is 18, and the difference is 7. So 9 goes into 70 roughly 7 times, which is 63, and the difference is 7 again. This will be a repeater. All right. So 12.9 repeating, 12.7 repeating. Right. That means that your Celsius is approximately, let's round it to a whole degree. Right. Approximately 13 degrees Celsius. Right. Unless they specify that they want it as a, the tenths place. Right. In which case I would make it 12.8. Right. Tenths. Okay. Let's do the other type. Let's say you were going to convert, this will be example 5. 60 degrees, I wrote it in a funny way, yep. Celsius is equal to so many degrees Fahrenheit. Let's see, if the formula is for Fahrenheit 9 over 5 times C plus 32, right? Because of the fact that there is no parentheses here, and we must follow the order of operations if we're just sticking with the right side here, do the multiplication, right? And it's understood that these two things bunched together are being multiplied. So plop 60 in here, and you could do brute force top times top, bottom times bottom, or use your calculator, but I would try to simplify always before I multiply. So the relationship between 5 and 60 is known as they're both divisible by 5. They both have a common factor of 5, that's the GCF, so this would be 1, and this would be 12, which means that this would be 9 times 12, and therefore the leftovers, since the denominators are just 1, is 108. All right, 108 plus the 32 that is here leaves you with what? 140 degrees Fahrenheit. Right, not too shabby, right? Okay. All right, that's it for today. All right, if you're following along, all right, remember, for homework, all right, do section 7.3 in my lab. And tomorrow will be the last day of the week, so we'll be covering section 7.4. Okay? Thank you guys for sticking with me. I will see you tomorrow. Be careful out there.